So next we shall move on the theorem 2. So the theorem 2 states that if f of z has a pole of order m at z is equals to a, then prove that residue of f of a is equals to limit as z tends to a 1 divided by m minus 1 factorial into mth derivative, m minus 1th derivative, that is what with respect to z. So d raised to m minus 1 divided by dz raised to m minus 1 with z minus a whole raised to m into f of z. So we need to prove this one. Proof. Suppose f of z has pole of order m. In statement only they have given f of z has pole of order m at z is equals to a. So that f of z is expanded as like this: f of z into z minus a whole raised to m is equals to phi of z. So here phi of z is analytic and phi of a is non-zero, right? Therefore f of z can be written as phi of z divided by z minus a whole raised to m, right? So residue of f of z at z is equals to a is b1. Residue of f of z at z is equals to a is b1, where b1 is residue of f of a. So here residue of f of a we have denoted as b1. So b1 is equals to, according to the Cauchy's theorem, what we have 1 divided by 2 pi I integration over c f of z into dz. Already we have discussed this theorem in regular classes. So using this formula 1 divided by 2 pi I integration over c, already we know that f of z is phi of z divided by z minus a whole raised to m. Put this quantity in this f of z is equals to. So here we'll get this quantity, and next 1 divided by m minus 1 factorial into m minus 1 factorial divided by 2 pi I integration over c phi of z divided by z minus a whole raised to m into dz, right? So this, why we have taken this? This is the formula for Cauchy's formula for higher order derivatives. So therefore b1 is equals to 1 divided by m minus 1 factorial into phi raised to m minus 1 of a. Yes. So this is equals to, b1 is equals to limit as z tends to a 1 divided by m minus 1 factorial into m minus 1th derivative of this quantity with respect to z. That is what? D raised to m minus 1 divided by dz raised to m minus 1 z minus a whole raised to m into f of z. So phi raised to m minus 1 of a, we have phi of z is equals to what we have here. Phi of z is equals to what we have, f of z into z minus a whole raised to m. So here phi raised to m minus 1 of a is there. So here we'll get this quantity. Therefore b1 is equals to residue of f of a is equals to limit z tends to a 1 divided by m minus 1 factorial d raised to m minus 1 divided by dz raised to m minus 1 and z minus a whole raised to m into f of z. So this is residue of f of a. So this completes the proof of second theorem. Next theorem is theorem 3. What it states: if f of z has a pole at z is equals to a, such that f of z is equals to phi of z divided by psi of z, where psi of z is equals to z minus a into f of z and psi of a is equals to 0, then residue of f of a is equals to phi of a divided by psi dash of a. We need to prove that. So proof of this theorem is like this. By theorem 1 we have, so by theorem 1 means here the theorem 1 states that if f is a simple pole at z is equals to a, then we have a residue of f of a is equals to limit as z tends to a, z minus a into f of z. So call it as equation 1. Now by Taylor's expansion or by Taylor's theorem, we have this quantity. You need to apply for both the functions phi of z and psi of z. So here if you apply the Taylor's expansion for phi of z, we'll get phi of a plus z minus a divided by 1 factorial into phi dash of a plus z minus a whole square divided by 2 factorial into phi double dash of a plus z minus a whole cube divided by 3 factorial into phi triple dash of a, and so on. Similarly, we can write it as psi of z is equals to psi of a plus z minus a divided by 1 factorial into psi dash of a plus z minus a whole square divided by 2 factorial into psi double dash of a plus z minus a whole cube divided by 3 factorial psi triple dash of a, and so on. Therefore, from above these two arguments, we can express this equation 1 as residue of f of a is equals to limit as z tends to a, f of z minus a into, in place of f of z you need to put phi of z divided by psi of z. So already we have by Taylor's expansion phi of z is equals to this one and psi of z is equals to this quantity, right? So here by putting phi of z and psi of z values, we'll get limit as z tends to a, z minus a into phi of a plus z minus a into phi dash of a, and so on, psi of a plus z minus a into psi dash of a plus z minus a whole square into psi double dash of a, and so on. So limit as z tends to a, z minus a divided by, so here if you take z minus a as common, 1 divided by z minus a. So psi of a is 0 over here, right? Already we have taken psi of a is 0. In the statement only they have given psi of a is equals to 0. Therefore we have taken 0. So if you take z minus a outside, what will get? Psi of a, here will get psi dash of a plus z minus a into psi double dash of a, and so on. So z minus a and z minus a are get cancelled, only will remains with this quantity, right? So if you apply the limit over here at z tends to a, what will get? Psi of a will remains, right? And psi dash of a will remains. What will remains? Phi of a divided by psi dash of a will remains. So here all these quantities will be 0. So what will remains? Residue of f of a is equals to psi of a divided by phi of a divided by psi dash of a. So this completes the theorem 3. Thank you, dear friends and students. So in the next video we shall concentrate on problems or examples on these residues, calculations of residues.